Hey guys, this is video 5.4, drawing covalent bonds. This is actually going to be part one. When I was trying it earlier and the app stopped recording, I realized, hey, it's a pretty long video, so there's a lot of information that's going to be covered here. Drawing covalent bonds is much more challenging than drawing the ionic bonds. It's still a process, so make sure you follow the steps. But this is going to be part one, so kind of let you break it up a little bit easier, and then we'll come back and do part two as well. So we're going to just jump right in. We're going to be starting on page 13, and I went to page 14. There we go. All right, page 13. So kind of just some brief basic things, then we'll kind of get into the more specifics. So Lewis dot diagrams for covalent compounds. These are going to be similar to ionic, but they're going to be different at the same time. So remember back to the other video, ionic bonds, what's happening with the electrons? Transfer of electrons, hopefully, is what you were thinking. Covalent compounds differ because there's only a sharing of electrons. And because there's this sharing of electrons that takes place, we have some other things that we've got to take care of, right? Where the transfer, one gave away, the other one took those electrons in. So it's pretty simple to balance it out. Here with the sharing taking place, there's other things we got to account for and think of as well. So it's kind of step one, write out your element symbols, draw their valence electrons, same as we did before. So I've got two hydrogens here in water, and I've got one oxygen atom. Okay. If there's more than two atoms, you're going to find the element with multiple unpaired valence electrons. That'll be kind of your central atom. That's a good rule of thumb. We're going to see it in the next page as well. Kind of typically, it's going to be the first one in your formula, unless it's hydrogen. Hydrogen, remember, can only have two valence electrons because it's in that first energy level, so it can only have one bond. But look for the one that has multiple unpaired valence electrons. You'll see things like carbon, silicon. Those are going to be really good sharers. They'll be the central atom a lot. Nitrogen, phosphorus. You'll kind of see as we go along here. It'll make more sense. So step two, we're going to draw dashed lines between the elements, and we're going to connect all lone electrons. We're going to try to pair up all the unpaired ones. So we've got one here that's all by himself in hydrogen, and we've got another one that's all by himself here on oxygen. Okay. So we're going to just draw a line to connect those, and that's a bond. Notice how many electrons were in that line, right? You had one for hydrogen and one from oxygen. All right, so there's two electrons in a bond, right, in a line. So we're going to do the same here, because again, they're all trying to get to 8. And one thing you want to stress is that 8 is great, but what does that mean exactly? Well, it means that they're stable. Okay, that's the key term, is that they are stable. So they're trying to get to 8, they're sharing or giving them away. In this case, with covalent, they are sharing. Okay, so we could then make it look something like this. And we'll go through all this, kind of the ins and outs of the different ways. It's just one general way to kind of show what's happening. So we can kind of say, hey, one dash or line between atoms is a single bond. Okay, so if you think about it, well, how many electrons then are being shared? So if you think about that, like we showed before, there's really one electron at each end of the dash or at the end of the line. So there's two electrons that are being shared, one from the carbon on the left, one from the carbon on the right. So there's a total of 2 electrons that are being shared. Now, how many pairs are being shared in a single bond? Well, pair means 2, so there's 1 pair. So make sure you note that with multiple choice questions, what the Regents will do is it'll try to trip you up asking things like pairs or total number of electrons. So make sure you read the question carefully. If we have 2 dashed lines between an atom, it's called a double bond. Okay, and again, if we drew those in, electron, 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 how many total electrons? You've got 4 being shared for a total of 2 pairs. And the last possible type bond you could see would be a triple bond. There's no reason why I'm doing it in different colors. I was just trying to get a red so you could actually see it here with this blue. All right, so there's 6 total electrons being shared for a total of 3 different pairs. All right, so that's kind of just the basics. Let's jump in and kind of go through the whole process. Really, what you're going to have to be able to do with drawing the structures, and there's a lot of different rules. It's a process. It's going to take practice. So if you have questions, ask me in person. Pause the video. Ask those questions as you come up with those. So the first example we have here, this really should be a lowercase 3. All right, that's a typo. I'll change that in the future, but just make that note. Okay, we're going to draw the Lewis structure for iodomethane, CH3I. Step 1, determine the number and types of atoms. Really, steps 1 and 2 I kind of do together. So what I mean by that is how many carbons do you have, how many hydrogens, how many iodines. That's the number of atoms. And the total number of valence electrons is really the first thing we want to do. So you're going to see me with all the examples that I show you. I'm going to write out the total number of electrons. You've got to be organized, and you've got to keep track of those electrons. Every electron that we account for in the beginning has to be used in our structure. If you have any left over, you've done something wrong. If you run out, we'll talk about what happens when you run out of those as we progress through this video and part 2 as well. So here we go. All right, carbon, I've got one of those. Carbon brings 4 valence electrons. I've got 3 hydrogen atoms. Each brings 1 valence electron to the party. And then iodine has 7. So I want to add all those up. 4 plus 3 plus 7, all right, is going to be 14 total valence electrons. So that means I have 14 electrons that I've got to account for in my structure. So there's steps 1 and 2, figuring out how many valence electrons I have. Step 3, we're going to form a skeleton structure. Typically, the first atom is going to be the central atom unless otherwise specified, or hydrogen's first. Now, just a side note here. Oh, I don't know what just happened. Sorry about that. Hydrogen can only have 2 total electrons connected to it. Okay, meaning only 1 bond. And I put that in all, well, I didn't write it in all caps, but exclamation points. You've got to remember that, guys. Hydrogen can only have 1 bond. Every year, no matter how much I stress that, I see students have more than 1 line connecting hydrogen to something else. It can't. It can only have 1 bond. So once you put a dash between it, notice all the examples I've already shown you, they only have 1 line between the hydrogen and the other atom that it's bonded with. Okay, so if it's the first one, go to the second one. If you see something like carbon or silicon, those are 4 valence electrons each. They're great shares because it's easier to gain 4 or lose 4. Who knows? It could go either way. So carbon's going to be our central atom. To make our skeleton structure, I'm just going to draw or write all the other element symbols around it. Doesn't really matter the order. I typically start at the top and go clockwise. So those are my 3 hydrogens, and then I've got an iodine. Now the last part of the skeleton structure is I'm going to draw 1 bond, 1 dash between each atom, okay, connecting it to the central atom. So now I've got to account for those. These are bonding electrons. How many do we have in there? Well, if we think back, how many electrons does a dash represent? You don't have to draw them in, but I'm just doing it with this first one to kind of show you guys that they're sharing electrons. These electrons right here that I'm circling, those are the ones carbon normally brings, okay? And then each the other ones it's connected to, the other atom supplies. So they're sharing. It's a it's not a give and take. It's a mutual coming together so that everybody can be balanced out, okay? Keep track of those. There's 8 electrons. I'm going to subtract that out from my total. These are my bonding electrons, okay? So now I have 6 more electrons that I still have to account for. Okay. Now again, what's everybody trying to get to? Everyone's trying to get to 8, except for which element? Hydrogen. Hydrogen's going to be happy with 2. So if I take a look at each element so far in my structure, that hydrogen's happy because it's got 2. This hydrogen's happy because it's got 2 electrons near it, and this one. So all my hydrogens are satisfied because they have 2, which is the most that they can hold. Now carbon has got 2, 4, 6, and 8. So carbon's happy. Iodine, though, when we look at it, only has these 2. Look at step 4. We're going to add unshared pairs of electrons so that each atom's surrounded by 8. Well, I've got 6. How many more does iodine need? Oh, look. That's going to work out perfectly in this case. Now iodine has those 8 all around it. We've got the 2 that I've already circled, 4, 6, and 8. Okay, so that takes care of my last 6. 0, that means I've used all of my electrons that I had originally counted, and that means my structure is good right here. Let me erase that. This is what iodomethane would look like. Okay, make sure that every atom is satisfied with 8, or in hydrogen's case 2, before you move on. Now, I know I went through that a little quickly. If you guys feel good, pause the video, practice ammonia and silicon tetrafluoride on your own, and then you can replay it to check and see if you did it right. If not, go with me and do another example or two, okay, before you guys try on your own. Let's go through that same process. So, find out how many electrons total first. We've got 5 from nitrogen, then we've got 3 hydrogen atoms, each brings 1. That's going to give us a total of 8 electrons that we have to use. So that's steps 1 and 2 are right there. Step 3, get the skeleton structure. What's my central element going to be? It's typically the first element. Unless it's hydrogen, then you go to the second element in your formula. So nitrogen is going to be my central. Again, it doesn't matter right now where you put these other atoms, and when we get to the Vesper stuff in another note video, we'll talk about that. Right now, we're just trying to get the basics down. Okay, step 3, finishing that up, get my skeleton structure. So I've put in 6 electrons that are bonding. Okay, so now I have 2 left over. These last 2 are going to be used with lone pairs. Well, let's see which element doesn't have all of its electrons. This hydrogen's good, it's got 2. This hydrogen's got 2. All my hydrogens are satisfied with 2. Nitrogen has 2, 4, 6. So where are these last 2 going to go? They're going to go right up here. And now nitrogen has 8. Okay, and we've used all those electrons. Kind of, again, keep that, make sure that you use it up, keep track of those. We use every single one. Okay, if you feel good at this point, pause it, try silicon tetrafluoride on your own. If not, I'm going to go through it. So again, same process. Silicon has 4 electrons. We've got 4 fluorine atoms that each have 7 valence electrons. So that's a total of 28 electrons. That's a lot to keep track of, so make sure you keep track of it as we go along. What's going to be my central atom? Silicon's first. Put that in the middle. Each fluorine is going to be all around silicon, and I'm going to connect them all with a bond. How many electrons did I just use? I've got 4 bonds. That's a total of 8 electrons. So I've got 24 other electrons that are going to be considered lone pairs. Okay, well, silicon has got 8. Okay, so silicon's happy. So now I need to get all my fluorines to be happy. Each fluorine only has 2 electrons right now. We got to make sure they get to 8, so they need 6 more. So there's 2, 4, there's 6. Now it's satisfied. 2, 4, 6. That one's all good. Keep track. How many have I already used? 2, 4, 6, 8, 10, 12. I need 6 more there. This guy's all good. That's 18. And there's my last ones. There's 24. I've used them all. That's what silicon tetrafluoride would look like. So, at this point, whether you feel confident or not, go through, pause the video, go through and try to solve Bri and CH3Br. All right, so hopefully you tried both of those. Let's start jumping right in. Notice you might have gotten stuck a little bit here with bromine and iodine. Okay, bromine's got 7, iodine's got 7, so it's a total of 14. You might have gotten stuck thinking, oh, well, I don't know what my central atom is. Guys, if I only have 2 atoms, there's not a center one because there's 2 points, so it's just going to be a straight line between them. So it doesn't really matter where you go with it. Just set them apart, go through the process from there. There's 1 bond minus those 2 bonding electrons. So I've got 12 others. Well, look at here. Each of them needs 6 to be balanced out with 8. And that takes care of my other 12. Bam. That would be my structure for Bri. Over here, same thing. CH3Br if you've done this already, it should look very similar to this iodomethane, because the only thing that changed up is the halogen that we've had. So 4 plus 3 times 1 plus 7. We have a total of 14 electrons that we've got to account for in our structure. Carbon's going to be in the middle. Again, just move your other ones out. We'll talk more about specifics as to where things go later on in the next video. Connect them up. So that's going to be 14 minus 8. I have 6 left. Each hydrogen is good because it can only have one bond. The other 6 then are going to go around bromine. And there's what our structure for bromomethane would be like. Okay? So, what you guys can do now, I'm going to pause this video. This is, like I said, part 1. There's other specific things. Well, what if we run out of those electrons before everything's satisfied? So go back, check out part 2 for the rest of this.